All right, today's notes are going to be called solving exponential and logarithmic equations. First, take notice that it is not just a solving logarithmic equations. It actually includes exponentials. All right, now this might be the last set of notes that we do with logarithms. And if it is, it's going to be a very fitting set of notes because we introduce logarithms as being a function that has to exist as the inverse to exponentials. We created this guy, okay? And if at the very end of our unit, we can actually cycle back and show how these work back and forth together to solve problems, then it's great. It's perfect. All right, now, as I mentioned, a logarithm is the inverse of an exponential function with the same base. I didn't actually say that part with it being the same base, but it is. And one of the early things that we learned about functions and inverse functions is that if you build compositions of them, you get back x. That happens to be a way that you can test them out. Because one function does something to x, and its inverse will always be the thing that undoes it. And if it undoes everything, aren't you going to be right back to where you started, which is called x? Okay, so with that, as an idea that we already know, this is what it would look like when you build these. Let's see here. My f function is going to be the exponential, g function is going to be the logarithm. So if I put f of x into g of x, it looks like this. I have a logarithm base b, and that x is going to get replaced with the entire function of f of x, which is b to the x power. This is what it looks like. I'm about to write parentheses here. No, I'm not going to do it because they're not normally there. But all of this is the input to that logarithm. Now, you might not be able to see here why everything cancels out, but it goes back to the idea of what inverse functions are and that their compositions should undo everything. So if you do see this structure, log base b of b to a power, you get back your exponent. That's how it works. All right, now the other way, put the logarithm into the exponential, and it looks like this. You get base b raised to the log base b of x. Now, again, we might not understand why all this stuff's going to cancel, but it's the concept of inverse functions, that if you put two inverse functions as a composition, you get back your input. So you get back x. So what you want to know is that when you see these structures, you can just simplify it straight down to x. Let's take a look at example 1. 10 to the log of 4. Now remember, what's important about just a log? It has a base of 10. So this is actually 10 log base 10 of 4. So that fits this structure here. Those numbers are the same. Whoops, I wrote an x, but it's actually going to be 4. So the whole thing's going to simplify down to 4. Now here's how the other one looks. You got a log of some base of the 25 of the x. Well, wait a minute. Let's talk about this. 25 is actually just 5 squared. So this is really log base 5 of 5 to the second power, but then you've got the x, so it's actually the 2x power. Now you got to be careful about that part, because if this is raised to the x power, you actually have a power rule, and these multiply to give you 2x. So the whole thing is going to simplify down to 2x. Examples 2 and 3, what we're going to do is use the concept of inverse functions to solve these problems. So what we start with here is it's 4 to some power is going to give us 11. Now, obviously that number is not like 16 or 64, some obvious number that you can get from raising 4 to a power. So we find ourselves, maybe one of the first times here, in a situation that's really like perplexing. Like, okay, what kind of exponent's going to give you that? We know that it's more than 1 because that'd give you 4, but it's also going to be less than 2 because that would take you up to 16. So it's somewhere between 1 and 2 here, but we need to know what it is. Okay, so here's the trick. Use logarithms to undo things. All right, and when you use the logarithm, just make sure that you use the logarithm in the same base. So I'm going to take log base 4, because it's the base that I have here, of both of the sides. In this case, I'll write the parentheses just so you can see that I'm like putting everything into a log base 4. Okay, and then to balance, the other side, you're going to put all of that into the logarithm as well. You have to be fair to both sides. Okay, but what's cool about this is here, that all cancels out. That fits what we've got up here. So it all simplifies down to just being x, which is great because that's what we're trying to solve for, and it tells us that that's what x is equal to. Right? So now, all right, after a little bit of typing, there it is. Something between 1 and 2. Actually turns out to be 1.7, whatever you want to round it to. Let's do 1.73. We'll say it's approximately 1.73. But look at that. Exponentials and logarithms are inverses of each other. So if you need help solving an exponential, use a logarithm to do. All right, example 3. This is in a logarithm. This is the natural log, which is base e. So if you were just to create exponentials out of these things by using a base of e, you can cancel out stuff. So we're going to do e as a base and make all that the exponent. Then the other side is going to be e to the 6th power. And again, everything's fair because if the left side is the same thing as the 6th, then as exponents to e, that should be an equivalent equation, like, still a balanced equation that we have. But remember that the natural log is log base e, so that you could visualize it this way. The natural log is log e. So all that's going to cancel out. You just get back the x plus 2. Now over here, that's where you're going to get that kind of crazy decimal number that could happen in these types of questions. And to finish this, you just subtract a 2 from that side. So you get e to the 6 minus 2. That's not a bad way to represent the answer because it is an exact answer, sort of like that would be an exact answer, but I don't normally state the answers that way, so I'll just go ahead and type it in. Let you take a look at it. And you get this. You get 401. We'll do 2 decimals again. 0.43. So, you know, it is what it is that you're going to end up getting from these guys. All right, at the bottom here it says, notice that examples 2 and 3 can also be solved by rewriting. So I thought this was a really neat thing to show you here is that a little bit earlier when we talked about the definition of logarithms, you can switch back and forth between exponentials and logarithms. So if I were to look at this equation, I could introduce a logarithm, use that base, then switch these two things around. And look, you get the answer. That's right there too. And so different ways to go about it, but nice to see how it all results in the same thing here. All right, now for this one, a little bit trickier probably to write it. I'm going to rewrite it as log base e of the x plus 2, so I can see the base, is equal to 6. So then I cover up the logarithm, and I write e to the 6th power is equal to x minus 2. And, plus 2. Sorry, is going to be plus 2. So then that's, where'd you go? That's this one right here. So if we just subtract the 2 from that answer, then we're done. So neat to see the definition does show up in the same way that we use the inverse functions to solve. All right, example 4 is going to basically do what I just talked about after 2 and 3, that you can just do like a little switch if you want. You can do inverses, like you can like make a 5 the base to each of the sides if you like that method, or if you like the switching method here, you cover up the logarithm and we take 5 to the 3rd power is equal to 5x minus 1. From that point, it's pretty much straightforward. 5 to the 3rd power is 125. You're going to add 1 onto it, which gets you to 126. Divide by 5. And I should be able to do that as mental math, but 25.2 maybe. Let's see what we get. Divide by 5. Yeah, 25.2. I think that's what it said. All right, so you can do the little switch, or you could do what was demonstrated in 1 and 2. I might have referred to them as 2 and 3 a little bit earlier, but is that right? Yeah, it was 2 and 3. That was good. All right, number 5. This is going to go back to using the properties. So there's a whole bunch of different ways of like solving problems and different techniques that you have to use, and this was introduced in the properties of logarithms. You have 2 x's in different logarithms. You're going to want to combine those together. In this case, because you've got the adding, like what we saw in the last one, you're going to use what's called the product rule. So we're going to have log of 8x. I'm going to be careful how I write this, so I'll just explain what I mean by it. Okay, all of this is going to be within the same logarithm. I just don't want to make more brackets around it. But these get multiplied together and gives you one thing that's in there. We do have a log base 10 when it isn't written. That's going to be important because now when we do our switch, you're going to get 10 to the 3rd power is equal to this. I think I'm going to have to multiply it anyway, so I'll just go with that. 160x. All right, so 10 to the 3rd power is 1,000. So this will become a quadratic. We'll start with 1,000. We got 8x squared minus 160x minus 1,000. That's going to have to subtract to go to that side. And then, I don't know, you want to factor that one? Well, these are both divisible by 8. That should be divisible by 8. Come on, fingers crossed. Yes, it is. So you can just divide 8 across the whole thing here. You get x squared minus 20x. Same thing that we saw over there. Minus 125. You still had to go through the whole process to get here, though. All right. 2 things that multiply to give you 125 and add up. 2 things that multiply to give you negative 125 and we'll add up to give you negative 20. That should just go back to all your 5s. You should have negative 25 and a positive 5. See if that's worked. That works. Product is negative 125. Together they give you the 20. So answers include 25 and negative 5. But again, if you go back and you plug this in, you remember this from the last thing that we did. The negative 5 is going to be no good in either spots because that'll give you negative 40 and that'll give you negative 25. But a 25 is good because you'll get 200 and you'll get a 5 for that. All right, let's just check it because I want to make sure I got this right before I publish this video. You got log of 8 times 25. That's the answer I'm claiming here. Plus the logarithm of 25 minus 20. And yay, we get 3. All right, so all is good. All right, so up last, I've got something that I refer to as cool trick number 6. If you're in one of my classes, then you've heard of cool tricks 1 through 5 already. They've popped up on occasions. These are not tricks that I just make up. These are things that I observe as being really neat techniques that you can use for answering problems. So they're not my ideas, but I do give them these names to them. Okay, so you have an exponential. That's the situation. You have an exponential, and it's going to be some weird decimal number. That's going to be the answer. Okay, what you can do is you can actually choose to use any logarithm you want. You don't actually have to take log base 4 which is what I did in, I think it was problem number 2. Yeah, you don't actually have to use log base 4. You can use any logarithm you want. So, and one of the reasons this is really cool is because depending on the type of calculator you use, like here, you can choose any base you want. But on most standard, like cell phone calculators, you can do a natural logarithm or you can just do a common log. Even if you can choose your own base, it might be a little bit messy. So what I always do is just use the natural logarithm. And I've created this as a way to solve problems just all the time. And it actually gets a little bit tricky trying to describe them in the other methods here because I'm used to just doing the problems like this. So here's what you do. You just take the natural logarithm of both sides, like that. You then apply the power rule for logarithms, which said that if you have an exponent inside the logarithm, you can move that to the front. So you get x natural log of 4 equals natural log of 11. Now here's the hardest part for us to really understand. The natural log of 11 is a number. That's it, it's just a number. The natural log of 4 is also just a number, right? They look like they're more going on, but they're just numbers. So if I've got a number multiplied by x, I can actually just divide that number away. And x is equal to the natural log of 11 over the natural log of 4. Do not cancel the natural logarithms. Just don't do that, okay? But here's your answer. Let's see if we get the same thing as the front. So and the reason I use natural logarithm is because it's a button right there. It's just such a fast way to do it. So I do natural log of 11, divide that by the natural log of 4, and you get that answer. Sorry, you couldn't see that. You get that answer. There's the division. You get that answer, which is right there. Now, it might look like a lot of steps and a bit to follow, but when you really summarize it to yourself, it's like if I have to solve an exponential, you can just take the natural log of that side divided by the natural log of the base, and you get your x.